Modern artificial intelligence can simultaneously ingest and output entirely different forms of data. Within a single mathematical system, the same core weights can generate functional computer code, coherent natural language, and high-resolution images. Artificial intelligence has transitioned to the foundation model, a general-purpose architectural substrate designed to be adapted to a vast range of downstream tasks. This is not a simple matter of training old algorithms on more data. It represents a fundamental architectural change in how software is engineered and deployed. These models rely on self-supervision, learning rich statistical patterns from vast oceans of unlabeled data rather than human-coded rules. To understand the implications of this shift, we must trace its structural evolution, from the software frameworks that automated deep learning math to the transformer architecture, multimodal scaling, and the systemic risks of a homogenized AI infrastructure. Foundation models have become the new infrastructure of modern intelligence. Grasping their capabilities requires us to look at the specific structural pivots that enabled their growth. In the early years of deep learning, building a neural network was a bespoke, manual process. Developers had to handwrite the complex calculus required for both forward and back propagation. Manually deriving the math for every neural layer created a massive scaling bottleneck. Any increase in model complexity required a corresponding labor-intensive increase in mathematical derivation. AI development only accelerated with the release of deep learning frameworks like TensorFlow and PyTorch. The breakthrough mechanism in these frameworks was automatic differentiation. This allowed the software to calculate gradients and update model weights instantly. Mathematical complexity was completely abstracted into standardized, modular computational graphs. By automating the calculus, frameworks allowed researchers to pivot away from low-level math and focus entirely on designing massive intelligence architectures. Even with frameworks, a structural limit remained. Before 2017, processing sequential data like text or speech required recurrent neural networks, or RNNs. The fatal flaw of the RNN is that it processes sequences one token at a time. To understand the 10th word, the model must finish processing the previous 9 in strict linear order. This sequential dependency caused vanishing gradients and made hardware parallelization impossible. This created a mismatch with modern hardware. Graphics processing units, or GPUs, derive their immense speed entirely from executing thousands of operations in parallel. The bottleneck was broken by the 2017 transformer architecture and its defining mechanism, self-attention. Self-attention calculates the mathematical relevance between every token in a sequence simultaneously. Instead of a step-by-step timeline, the transformer treats sequence processing as a single, massive matrix calculation. By removing the temporal bottleneck, model training could finally be distributed across massive clusters of GPUs. The transformer turned sequence processing into a geometry problem, allowing model scale to grow infinitely alongside hardware capacity. Parallel processing enabled foundation models to scale to hundreds of billions of parameters, ingesting unprecedented volumes of global data. At this scale, models develop emergent capabilities. They spontaneously learn to perform tasks like zero-shot translation or in-context reasoning that were never explicitly programmed into their training. This happens through representation learning, the model's ability to extract reusable patterns from raw data. The model embeds disparate data types into a shared high-dimensional coordinate space. Statistically related concepts group together here, whether they started as text, pixels, or sound. This alignment inherently supports multimodality, translating between formats using pure geometry. Researchers are now leveraging this to map biological signals, like fMRI brain scans, into the same latent space used for text and images. By aligning neural activity with visual and linguistic representations, generative AI can decode semantic imagery and text directly from brain scans. Scale has transformed these models into cross-modal engines, capable of reconstructing complex semantic meaning directly from biological neural activity. While these models are powerful, their size is a deployment barrier. Retraining a foundation model for a specific industry task is too expensive for most developers. The solution is low-rank adaptation, or LoRA, a technique for parameter-efficient fine-tuning. LoRA freezes the massive pre-trained weight matrix of the base model. A parallel pathway decomposes the update into two highly compressed, low-rank matrices. This slashes trainable parameters by orders of magnitude before merging back, resulting in a customized model with zero latency. LoRA makes it economically viable to deploy localized, high-performance versions of massive models across every sector of the economy. This efficiency hides a growing liability: algorithmic monoculture. Thousands of diverse applications across healthcare, finance, and law now rely on the exact same handful of foundation base models. Any intrinsic bias, flawed data, or representational erasure in that base model propagates instantly to every application derived from it. A single successful data poisoning attack on a foundation model creates a universal vulnerability across the entire ecosystem. Because these models learn through emergent representation, their internal logic is nearly impossible to fully audit, leaving us with powerful but opaque systems. Maintaining this homogenized infrastructure requires an ever-growing physical footprint of high-density cabling and cooling systems to manage the energy load. Foundation models have successfully mapped intelligence into a universal mathematical space, but our reliance on this unified infrastructure demands an entirely new framework for governance and global auditing.